Hello, I wanted to talk today about these techniques, which are for looking at the surfaces of materials. As we can see, there's one of them, that's clearly somebody's name, Auger, and the other ones are three-letter acronyms that begin or contain an X. The X stands for X-ray. They all have this sort of physical processes in common. So let's look at that. This is a Bohr model of an atom. It's quite a big atom. That's for a reason, because we're going to look at these inner electron energy levels. So the first step in all of this is that we have some kind of energy that we send to our atom, and we kick out an inner electron. This is the electron leaving. If we can control the energy perfectly, then we can use it to measure the energy level of this orbital by measuring the residual energy in this electron. That's what's hidden underneath XPS. The reason for the X-ray is that if we use a photon, the atom is required by quantum mechanics to absorb the whole photon. It can't just absorb half of it and give the rest out as light. It has to absorb the whole photon, and it has to do something with the energy. And in this case, it gives all of the energy to this electron, and the electron leaves with kinetic energy equal to the energy of the incoming photon minus the energy of this energy level. This does give us some difficult challenges. We need to have a monochromatic, a single color X-ray beam, so that we know exactly what energy we're putting in. That's not trivial because they're X-rays, so they're hard to manipulate. And we also need to measure the energy of this electron very accurately without it exchanging energy with anything, so this all needs to take place in a good vacuum. Otherwise the electron would hit some gas molecules on the way and maybe slow down. Independently of the type of energy that's used to create this electron hole in this orbital here, a number of things can happen, but the simplest one is that an X-ray can be emitted in which an electron falls from a higher orbital, that would be this one for example, drops into this hole. That obviously shifts the hole up one, and that is lower in energy, so it gives a lot of energy out. And the simplest thing that can happen is it gives out a photon of energy. If it gives out a photon of energy, that's typically an X-ray, and so that can be measured to tell us the energy level, but what it tells us is not the energy level compared to vacuum, which is what we were measuring before by shooting it out with an energy source, XPS. We're now measuring the difference in energy levels between this orbital, wherever the electron is, and this orbital, wherever the hole is. Then we get a photon out. That's typically an X-ray, and we're going to see that in EDX, which is when we've shot an electron in, typically. We have one of these detectors in our electron microscope, and it does exactly this. We fire in an electron to snooker this one out of the core orbitals, and that gives out a photon of X-rays, and that makes it comparatively easy because we're only looking for X-rays once. We don't shoot an X-ray in. That's another good reason for XPS as well, because if we shoot an X-ray in and look for electrons, that's good as well, because then we're only looking for electrons. If we consider the last case, XRF, that's when we shoot an X-ray to excite it, and we measure an X-ray coming out. So it's fluorescence because we have a delayed emission of a lower energy type of light, and it's X-ray fluorescence because we shoot in an X-ray to knock it out, and we get an X-ray back. But it's a different color X-ray, and we can use the color of the second X-ray, which has nothing to do with the color of the first one, to tell us something about the molecule. The good thing about both of these techniques is that the energy of the source that we used to knock out this electron is irrelevant. It just has to have enough energy to knock it out, because we're not measuring anything to do with this orbital. Then the electron that comes out carries any excess energy with it, so it doesn't matter. That's good for electron microscopes because it's hard to get a very, very tight energy source. a very tight speed of the electrons in effect, and it's good for X-ray fluorescence because then we don't have to worry about getting a single color X-ray beam, which is one of the problems with XPS, that is one of the things that makes that technique expensive. The other possibility is that the energy liberated from this process of an electron dropping from a high energy state into a lower energy state can be dumped into a third electron, which in this case is this one here. It doesn't have to be that one, and that will be ejected, and it contains a certain amount of energy that's equal to the difference between these minus the energy of this one. So it has a certain amount of energy that we can refer back to the original atom with. All of these techniques are good for identifying what atom we're looking at. They have different strengths and weaknesses. This would be the Auger electron, and obviously if we're looking at an electron coming out, there are issues involved if we use an electron beam to excite it. There are historic machines that do that, so there are ways of doing it, but it's comparatively tricky, so very often an Auger is not excited with electrons, but for some purposes, electrons are used. Obviously then we will have to filter out the bouncing electrons and secondary electrons and all kinds of things from what we're going to measure, but because these don't have directionality and the ones that we put in did, then we can do that to a certain extent. I nearly rubbed it out, but I will just keep half of the diagram for the start of this next theme. Because we've got an internal electron that we're knocking out and something else always happens, then we have to have internal electrons for any of these techniques to work. That means hydrogen is not visible with any of them. XPS is a little bit better because it works on the single electron being shot out, but the other techniques require two levels with electrons in them, so they don't work on the first row very well. EDX will work down to very light elements, but it struggles with boron, for example, because the X-ray is very weak and it's not very, so it's both low in energy and it's not very strong. X-ray fluorescence also struggles with boron, although it's often used to measure boron for practical reasons. It struggles to measure it because obviously there isn't much of that. Oops. Meaning that the probability of hitting the electron is low. What I wanted to say at this point was that as the atomic number changes, the probability of getting an electron, an Auger electron, compared to the probability of getting an X-ray, changes. So the lighter the element, the more likely we are to get an electron. This is the probability of getting an electron. And the heavier the element, the more likely we are to get an X-ray. Obviously this switchover is at 30, so it's like below the second group. But, second period. Obviously too, as I mentioned before, this curve, neither curve goes all the way back to 1, because element 1 hydrogen is invisible to all of these techniques. We need to have at least lithium, so it's got 3 electrons in it to be able to do Auger at all. And in X-ray we need at least 2 different shells to have one, which also means we have to be at lithium to be able to get anything at all. And as we can see, we get very little signal at very small weight masses in the X-ray region. So one of the considerations is which elements are we looking at, because the lighter elements are going to be more difficult to see in X-ray emission techniques, and easier to see in electron techniques. And the other way around, for the heavy elements, we'll be able to see heavy elements better with X-rays and worse with electrons. Which means that obviously if we're trying to measure lead, then X-rays are better, and if we're trying to measure boron, then electrons are better, but we don't always have that opportunity. After that terrible bit of stuttering, let's try it again. If we look at our X-ray fluorescence, we can see that for the technique we'll need some kind of container to stop X-rays coming out and irradiating us, and we will send our X-ray beam in and we'll get our X-ray beam from the X-ray fluorescence out. It won't be oriented in the same direction, so we can look at it from a different angle, and what we can see is the beam going in can be high energy, so it can penetrate through the whole thing, but depending on which X-rays we're trying to get, so how light they are, they can escape from different depths, either micrometers into the sample, but sometimes centimeters. So in soil it's centimeters for heavy elements. In glass or heavy items we might want to see boron, for example. In glass, boron is a typical element in glass, but then we're stuck at the surface because the X-rays that are emitted from boron are very low energy. Auger is much more surface sensitive because it's releasing an electron, so both Auger and XPS are way more surface sensitive because a low energy electron has much more difficulty escaping from deep inside the surface. It doesn't matter how we excited it, it's how it can escape that matters in that case. If we go to EDX, we're shooting in an electron, so the electron has to go down and the X-ray can escape comparatively easily, but that means that we are limited to the shorter thickness that we would have in X-ray fluorescence, and XPS is more a surface technique, as is Auger. Which matters because if we want to measure the bulk concentration of something, we're not going to do that at the surface for reasons that we've had in other courses. We will get enrichment of some chemicals at the surface, and they will be dirty, and there will be oxide, and there will be other material adsorbed to the surface that we will tend to see with surface sensitive techniques. And if we want to know the bulk concentration, we need to get deeper, but X-ray fluorescence requires a few tricks and a few references to be sure that you have the real bulk concentration, because we're measuring at the surface and deeper. X-ray fluorescence we won't think about too much because it is a bulk technique. It doesn't really look at the surface very well. So now we get on to the more interesting techniques, for the purposes of my surfaces course at least. EDX and XPS. EDX has a better surface sensitivity in the micrometers range, and XPS has an excellent surface sensitivity in the nanometers range. We can make it even better if we use other techniques, but this is what we've got for today. So process, to go over it again, is we first of all have an electron comes in, typically knocks out one of the electrons in our atom, and then a second electron drops into the hole and gives out a photon, which is what we look for. That has several physical important effects. First of all, the photon coming out doesn't care whether this atom is in a charged or uncharged environment, which is massively helpful if we're doing EDX in an electron microscope, for example, where we might not be able to control charging. We're shooting electrons in, knocking electrons out, so it may get positive or negatively charged, and that's a problem for XPS, we will see in a moment, because the electron leaving will be accelerated or held back, retarded, by the charge on the surface, either the atom or the surface, depending on what it is. That is not a problem with this case because it's an internal electron dropping down, so there's no change in charge, and a particle comes out that's unaffected by charge, a photon. So that's good. The other thing that is also an issue is that we're looking at the difference between two internal energy levels. Typically there are further energy levels out here, and any bonding goes on out here. The interesting and important thing about that is that if we bond our atom to something else, that will move the energy of these levels in or out. So if we bond an electron, we're effectively removing it from the atom, so all the other ones get closer to the core. But that has comparatively little effect on the difference between the energy levels, because we're measuring the difference between the energy levels here effectively. With this photon, it is comparatively unaffected. That's good if we don't know what we're looking at. EDX is an excellent technique for looking at things where we don't know what elements are in there, because it can identify them very well. It's very bad at identifying what they're connected to. So if we have an example of calcium carbonate or a calcium oxide with some carbon attached to it, in EDX it's hard to tell what we have. We can find out which elements are in there, but we can't tell which ones they're connected to. So if we're unlucky, we can end up with a particular constellation that looks like it might be calcium carbonate, but they're not actually connected to each other. And reminding you that we can't see hydrogen means that whether it's got an OH on it or not is completely impossible to tell. The reason that EDX is comparatively deep, it goes down micrometers into the surface, is that although we've got a not particularly high energy electron, it can penetrate reasonably deeply into our sample because it's the higher end. It must have enough energy to excite a core electron, and obviously the probability of hitting a core electron in the first atom that it passes is not very high. Those core electrons are comparatively tight to the nucleus, so it can pass several atomic layers before it is likely that it hits something. Likewise, an X-ray is leaving, and as we know from X-ray fluorescence, X-rays can escape micrometers even if they're pretty low energy, and they can escape centimeters if they're higher energy. They can go through materials fairly easily. Our familiarity with X-rays is more with medium power X-rays, and so those usually go through our body and are stopped mostly by heavier elements in bones. But they still go through. So in our EDX we've got an effect where our electron beam passes into our sample and it will escape, or it will excite X-rays that can escape from a relatively high depth, and there's a toss-up between which one, the electron or the X-ray, can penetrate further. Typically the electron is the thing that's being stopped. In fact, the reason that the electron microscope that we're using to do this has a comparatively better surface sensitivity is that the electron that we look at, the secondary electron that bounces off, can't escape as easily as the X-ray. So although the electron beam passes into our substrate, the one that we're looking at, the one that's escaping, either backscattered or secondary electron, has a lower energy and therefore it can't escape so easily. So we come to the depth sensitivity. This comes from the low energy of the electron that we're going to measure here, because it's not moving very fast, so it can't escape from very deep, and so we only get nanometer depth sensitivity. This is important because obviously if we have a metal, we're only going to be looking at the metal oxide. It's going to be a lot of nanometers, but still we'll typically not get through the metal oxide unless it's something with a very, very thin oxide layer. The electron has a low energy, and so it's also affected by the charging of the surface, so we have to watch out in X-ray photoelectron spectroscopy how we treat our surface. Ideally it wouldn't charge up, but if we coat it with something, which is what you do in electron microscopy, you can't even get to the original material. It also means that if we've got any dirt on the surface, that is what we will see. The second thing is obviously because we're probing the energy of one energy level rather than two, we're much more sensitive to changes in bonding, and so we can see to a certain extent what we're connected to. So we can tell whether we're an oxide or a hydroxide to a certain degree. We can tell the oxidation level of our metal ions. We can measure certain things and make conclusions from it. But the flip side of that is because our energy bands move around, we have a less confidence in what the elements actually are if we don't know what they are beforehand. So if we know what's in our sample, XPS is a better technique. If we don't know what's in our sample, there are better techniques. X-ray fluorescence and EDX are better to give us that information beforehand. Obviously, typically and practically, we often only have one technique and we have to misuse it for something that it's not ideal for. But if we were to have all possible techniques, then ideally we would put our sample into EDX first to see what elements are in there, maybe XRF to get deeper information, and an XPS finally to work out what is the organization of the elements in our material. So this is an example of an XPS spectrum. It's a free one with copyright free on Wikipedia, and what we can see is how it's typically drawn and what typical peaks look like. So typically we would go read from the left to the right, and we can see the binding energy as given is right to left. That is because the scale is effectively the energy of the electron coming off, so the binding energy is naught if the energy of the electron coming off has the same energy as the photon going in. That would be when we get it free, we just knock it off. And if it has the same energy as or the energy level that has pretty much the same energy as the photon that we put in, the X-ray photon, then it will just kind of flop out and have no energy at all. That's why the binding energy scale is backwards. It's the energy of the energy level where we've stolen the electron from, and it's backwards because it's really the energy of the electron. What we see is that we go over steps, so the background goes up and up and up, and then steps down again. That is fairly typical for these. So the step is because if we're going in this direction, get more and more energy to give away, we find that we can excite this electron, and then obviously we can give it more and more energy. So we can excite the electron, but if it's also moving or if there's also something in the way, we can excite it as well, so we get a tail on the peak. It's not a perfect zero thickness peak as we had in physical chemistry some time ago. What we can see is the peaks are labeled. There's not an Auger, is there here? There's an Auger peak. So this one here, OKLL, K stands for the K and L stands for the shells, unfortunately labeled KLM, and this particular one is an Auger peak, which we also see in XPS. This Auger peak would not change if we changed the color of the X-rays. These other ones do, so this is the O1s, the oxygen 1s electron that we're shooting out with our X-ray, and we would be able to find that and find out what it is. This is a survey spectrum, so we can not see what the oxidation state of these elements are. They shift around by the oxidation state and what they're connected to, but only a small amount. So typically if we did XPS, we would have to do this, which is a survey spectrum, and then take a zoomed in version afterwards. This is the zoomed in version. It's of oxygen, I think, and it's, oh, hang on, I'll check. Where is it? No, it's of silicon. So this is the zoomed in version of silicon, and we can see that they have done some fitting. These are curves that are fit to the actual measurement to be able to extract how much of a percentage of the silicon in this case is in different oxidation states. So we've got the various oxidation states of silicon, and we can see them in the shift of the peak for silicon, as long as we can be sure that we know where one is, because again we have to remember that if the sample charge is up, all of the spectrum is then shifted. This is EDX of a similar sample. It's also got oxygen and silicon in it, and it is, as you can see, the energy is the other way round. That's because it's the energy of the X-rays coming out, and they have less subtractions, and you can see we're also using the K letters, K, L, and M letters for the shell which the electron or energy came from, which the electron is dropping into. What I want to show you here is that there are several peaks for each element. So our iron has this iron K alpha, it's got a beta, that should be a beta, K beta, and it's also got an L, so that's an electron in a different shell giving out the X-ray. Depending on which one we use to define it, we can get more information out. Obviously we would typically try to take the peak with the most energy, with the most integral effectively, but we can see here, for example, the oxygen and the iron L overlap each other, and that is obviously a problem because we will have more and more difficulty extracting the real percentage of the oxygen in this particular constellation if we have more things underneath it. The silicon here is nicely silicon here, I was using the wrong mouse button. The silicon here is nicely away from the other things, so that's easier to measure. And what is also important is that the ratio between the sizes of the peaks is determined by quantum mechanics, and so that is pretty much fixed. So if we take this ion K alpha and the ion K beta, they should have a fixed relative height compared to each other, so we can, if we can measure one, we can simulate the other one, and so if there's something on top of this ion K beta, we can subtract it if we know how much iron is in the sample already, which is very handy. We also should remember at this point that although this sample has a comparatively high oxygen and carbon signal from before, you can't see my board anymore, from before, the probability of giving out an X-ray is comparatively low at lighter atomic masses, and that is obviously exciting and a problem for this technique because it is harder to measure lighter ones. What it means is that we would typically underestimate how much oxygen and carbon is in there because the peaks are smaller than the iron, for example. So although this oxygen is slightly bigger than the iron peak, there's probably a lot of oxygen in the surface of this sample compared to the iron because the sensitivity to oxygen is lower. The height of this band and the area of this band are comparatively low because the probability of exciting a photon, an X-ray, from our oxygen atom is lower than the probability of exciting one from the iron. What is important about EDX is there's comparatively little point in taking a zoomed in version of this, which is good because it saves time, but it's bad because we don't get any more information. It is very good for getting a gross analysis of what is there. But again, it is a slightly surface-sensitive technique, so the fact that there's carbon in our sample doesn't mean it's not just dirt on the surface. It's in fact almost certainly dirt on the surface of our sample and not to do with the bulk material, which is always something that we should carry in the back of our mind when we're trying to measure the surface of real samples. Getting on to the technicalities of how this is actually measured, let's have a look at EDX first. But the problems that we will see will be due to the problems of analyzing the energy of electrons and of dealing with X-rays. So here we have what would be our electron beam in the sample chamber, crossing over as a focal point, not necessarily at the surface of our sample. And we have some kind of takeoff for our X-rays, and the rest of the chamber is metallic. Where are the issues going to be? Well, first of all, we have a relatively small takeoff for our X-rays because we need to typically have all the rest of the electron microscope gubbins in there, so there's usually not very much space, so we end up with a very thin pipe leading to our measurement system. And for the problem of electrons, the problem of electrons in this case, we're trying to make an image of our surface, or that's what the electron microscope is capable of doing. And so we need to focus the electrons to a small point, but because electrons repel each other, it is better to keep them apart as far as possible and focus them at the last moment, and we get a better focus. So it means that it's better to focus them through a sharp focus than it is to have a parallel beam. Because it's a scanning electron microscope, I'm not going to explain how that works here, but because it's a scanning electron microscope, the size of the spot is the resolution, because it's going to measure at that spot and then move to the next one. It does that in the electron beam imaging mode, and it also does it in the X-ray imaging mode. For the X-rays, it's really handy because we get an image, although the image is less good than the electron image, because if you imagine we move the point up to the surface and we can get a reasonably good image with a tiny focal point. But if we look at the X-rays, we're looking at all of the X-rays down to here, because the X-rays can escape from a greater depth than the electrons can, and so our imaging resolution is way lower with the X-rays. The good thing about it is it's now immune to charging, so we don't need to coat our sample, which is an issue in electron microscopy. So now the issue is we need to measure these X-rays. The problem with X-rays is that they don't interact very well with matter. So it's kind of hard to measure them. And we need to measure the energy, so we can't just see that they're there, which is also a problem, because obviously if we had a photodetector, a standard photodetector, it would tell us that X-rays were hitting it, and we might get a count of how many X-ray photons are hitting it, but it's hard to tell the color, because we can't do what you would do in a normal camera, like I'm using here, which has effectively a color filter over each pixel, and just allows photons of a certain color through. That kind of filter is prohibitively difficult with X-ray photons. So what we would like to do is measure the energy of the X-ray photon. There is another issue, of course, because of the constellation that we have. We've got an electron microscope, so we're measuring point for point and moving around the surface. We need to be able to collect as many X-rays as possible from each point without moving the camera, and that means we're only measuring effectively on one position on the camera. We can expand the beam to have a lot of surface that we're hitting with our beam, but we can't get a direct image, because that's not how electron microscopy, scanning electron microscopy at least, it's not how that works. So we would be incompatible with the other system. What I've drawn here is a standard semiconductor, so just to remind you, the standard semiconductor has a Fermi band. It's got a band of, so this is the normal electron carrier band. It's got electrons in it, but they can't move around. It's got the conduction band, which is up here, and we might have some dopant in here, which are either doped with electrons or they're doped with electron poor things, so they either accept electrons from here, generating a carrier band in the center, or they donate electrons to the conduction band. That either gives us a P or an N-doped conductor, and that means that semiconductor in other words, and that means that we can either get conduct with holes in this band down here, or with electrons in the normal conduction band. The reason that I've got it here is that we're going to hit it with a light, and the light is going to excite some electrons. We're going to take this out because it's easier to explain without it in there. It may or may not have dopant in there, but we don't need to worry about that for this particular explanation. What we want to do is have our photon come along and excite some electrons, and the number of electrons will be a multiple of the electron energy. So there isn't already an issue. It's the same issue that we have with infrared detectors, that the photon resolution, in this case the energy resolution, in the case of infrared, the energy limit, the maximum that we can measure, the lowest energy that we can measure, is limited by the band gap, and ideally we'd make it as small as possible, but obviously if it's really small, we're just going to get thermally excited electrons that are going to jump up on their own. That's sucky, because then we'd have a lot of signal in the background that we'd have to deal with somehow. And so ideally we would cool this detector to stop that from happening. It's obviously still going to be affected by cosmic rays and things are zapping in it, but that is an issue that we can't avoid. If we have a small band gap, what it means is that when our X-ray photon comes along, it will excite a number of electrons, and then they will hang around in the conduction band and we can conduct with them. But in this configuration that I've drawn, they will just drop back down again because there isn't any reason for them, there's no motivation for them to go anywhere. So we have to generate a motivation for them, and that is usually done with an electric field. That's a common way to motivate semiconductors. Now what I've done is applied an electric field to my semiconductor, and I can imagine the electrons as being like little balls. They will tend to fall down or roll down this gradient to the positive electrode, and I can imagine the positrons, the holes in my other band. I keep forgetting what it's called while I'm talking. I can imagine the holes as little bubbles that are trying to float up, because they're going towards the negative electrode. It's just it's a consistent way of drawing it. If we have up being good for positive charges and down being good for negative charges, it allows us to draw the diagram all on one diagram without having to change the axes all the time. What it means is that I can put an ammeter on this circuit and count the electrons. I have to have a very accurate ammeter, obviously, because I'm counting individual electrons, but I can possibly do that. The problem that you may already have noticed, the issue that you may already have noticed, is that if two X-ray photons hit within enough time that the charge hasn't run out, then I will get the wrong energy. What this means practically is that I cannot have so many photons coming out that happens too often. Otherwise I will end up with too dirty data and it is impossible to clean it up. There are several ways to do that, physical ways to improve it and computer ways to improve it. So first of all, the physical ways to do it are I reduce this size as much as possible. If I do that and have multiple ones of them, then I reduce the time it takes to pull the electrons out, and so that means that I can measure faster. So the time that the two photons have to hit it is smaller if I have a smaller sample, and it also means that the probability that two photons hit it is lower, but I can still use parallel ones and get the same amount of data. The other thing that I can do is I can turn the beam down. So typically in a practical system you don't measure the X-ray spectrum at the same power that you measure your images. It depends on a lot of things. You often have to turn it up slightly. You sometimes have to turn it down to avoid two photons coming at the same time and overloading the ability of the computer to do the next step, which is to fix the spectrum. So then what happens is there is a running program all of the time that is looking for double, triple and quadruple the energy, typically just double, and it rejects measurements that are doubles, that are multiples, exact multiples of each other, because that is usually a sign that two photons have hit at the same time. But as I said, if we turn it up too much, that becomes a problem. It struggles to deal with it. But if we only have a small number of those events, it can work out how many there are supposed to be because of statistics and then remove those. That allows us to get a comparatively clean spectrum, but it's a complicated task to do it, and when you drive the machine, when you're given one to use, that's one of the issues to deal with, that you have to have the correct intensity of photons, otherwise your spectrum becomes less good. It becomes harder to measure. Because we're counting individual electrons and individual photons, obviously it is a time-consuming technique because the reliability of the process is low. We count one photon, that means we've got one piece of information, and as you saw, the peaks are smooth curves, so we need to measure a lot of those to be able to build a curve, which means that very often that you're waiting for some minutes, 10 minutes possibly. Sometimes if you want a good 2D image at reasonably high resolution, it can be hours, but typically it's minutes to get a good spectrum to be able to tell what is in there. Okay, the XPS is now going to be more complicated because we have to also explain how we make the X-rays, and to make the X-rays we have to make electrons, which we probably should have considered before. How do we make electrons? We're going to have a filament, which is a metal, because we need to extract the electrons from a metal here, let's call it M, and the electrons in the metal are stuck in there by effectively the work function of the metal, which is the energy that it requires to get the electrons out of the group metal orbital, that is the conduction band. That's the highest energy that we have in there, the highest energy electrons, and those are the ones that we want out. So we can do that by a variety of means. The two main ones would be giving it electrical energy and giving it heat. We can also shine a light on it. If we give it electrical energy, it's going to get more and more charged, and then we will be able to extract electrons with brute force. But we want some electrical energy because we want to accelerate the electrons, either to get energy in them to generate the X-rays for XPS, or just to get energy in them to do our electron microscopy in the first place. And that will also generate an X-ray in the end when we're doing our EDX. So we need lots of energy in our electrons, and that means that either we're going to have a lot of stages of electrical power that we're going to have to put in, or we're going to have one high electrical power, and so we don't want to have that as well. The other problem with electrical power is because we're going to have to charge this to a very high negative voltage compared to everything else, it's going to then be attracted, and if it's a thin piece of wire, it will bend and distort and get damaged. So an alternative way around it, well, two alternative ways around it, are to first of all reduce the work function of metal by choosing a surface that is comparatively low in work function. That would be a rare earth metal. So very often these metals are then coated with cerium or lanthanum to make them more easy to extract electrons from. It lowers the energy barrier, but also we make them hot. So here is an example. We have a filament, which is typically the inside of an old style electric light bulb, just a thin wire that we pass current through and it gets hot. I've called it AC, it doesn't really matter. But then we charge that up to a negative potential and extract electrons from it. That's effectively what the electron source is in the normal electron microscope. We can make it better by making it pointier, because that focuses the field from the charge, and so we can sometimes do it at lower voltage. So in an alternative instrument we would have a very, very tiny tip, nanometers in size, and that will generate field emission. So we just have an electric field and no heat. We can have a field emission source. For X-rays we need quite a lot of electrons in the first place, and so we can't do it like that. To generate a lot of electrons, it's better to have a hot filament because it makes more electrons. And we can then make the whole of the filament emit electrons rather than just a point. This is a bad configuration because obviously our electrons will cane straight into this positive electrode, and that is not going to be very good. The positive electrode has to be another metal because it is going to do something very similar to the EDX process to generate X-rays. So X-rays are going to be generated by electrons hitting the electrode and exciting electrons, and then other electrons falling back in, and that generates our X-rays. The problem is, well, the issue is that we generate lots of different X-rays, and there is another type of X-rays which are given a German name and there is no English name, Bremsstrahlung. It's when the electron goes into the metal and realizes quantum mechanically that it is past the speed of light in that medium. In a vacuum it can go quite fast. In the metal it can't go so fast, and so it's broken some laws of physics. To avoid that, it slows down, and the energy has to go somewhere. It slowing down gives out X-rays. Those X-rays have a broad spectrum. They're relatively high energy, but they have a broad spectrum of energy, and if we want to do XPS we need a single color. So that gives us the next problem. We've got our X-ray source. It's not like this because we need it's not like this because it would be impractical if the X-rays came out of the front here, because they would go straight into the filament, and that would cause all kinds of difficulties with organizing where all of the wires go and where the filament is. So we can bend the electron beam with a magnet or with an electric field and have it hit a different side of our electrode. Because the electrons have a very high energy and the process isn't super efficient, we also need to cool our electrode if we're going to get high energies out, high flux, a lot of X-rays out, because otherwise it will melt. It can get hot very quickly, partly because we always forget, because we live in the normal world. In a vacuum, it's hard for heat to get out of things, because conduction works in a vacuum, but convection does not, and that means that if we put 100 watts of heat into a filament, but we take very little of it out. It will get a lot hotter in a vacuum than it would in the air. That's good and bad, but in this case it's bad because we have to actively cool our anode. We have to, I'll start again, we have to actively cool our metal source of X-rays. I might have forgotten to cut that, but anyway, I was correct. This anode is the anode, so it's often called the anode anyway. But the reason that it's there is to generate X-rays, and the ones that we want are the single color X-rays from one of those bands that we would see in the EDX. But obviously, we need the high energy ones, because otherwise we won't be able to excite the electrons in the core of other atoms. Obviously, if we were going to use normal light, we would then split the light into colours and use one colour, so we would block all of this other ones. We would use a prism, for example, if we were low tech and old style, or we would use a diffraction grating if we had one lying around. The good thing about diffraction grating is its reflection or transmission, but the reflection ones are better. It's reflection, so we get a higher percentage of the light. We're not passing it through another material. The problem that we have with X-rays is that it's very difficult to choose a material now, because if we want to make a prism, there are not very many materials that bend X-rays very much. They typically go straight through, or they don't go through at all. Or we have to make a diffraction grating, and the problem with the diffraction grating now is that the line spacing has to be incredibly small to be able to diffract the X-rays by enough so that we can get a good angle on here, so that we can block the ones that we don't want, which is all the colours apart from the main line from the metal that we've chosen. Luckily, there is a natural source of things that are very close together in a very good order, and that would be a crystal. So we can use a clear crystal to diffract our X-ray beam so that we can split the colours of light. But we still have a problem, because in the drawing before, we were already imagining that we had a collimated beam. Collimated meaning that most of the light photons are going in the same direction and it's narrow. That's very handy for doing optics with, and we'll have thought about those most of the time. But we're generating our X-rays by whacking electrons into a metal, and that is going to generate X-rays that are going in any direction. It behaves like a small source if we hit it with electrons in a small point, but that's not going to be very bright, because we'd just melt it if we had too much. And the electrons go quite deep, and our X-rays can escape from quite deep, so we will be very hard pressed to get a good point source. And of course, if we want a good amount of electrons of X-rays, we're going to have to spread it over a large area. So to do so, what we really need is some kind of lens for our X-rays, which is a difficult thing to do. However, we've got our crystal. We know we can do diffraction with it. So what we can do, and what is typically done, is the crystal is bent, curved, and then it acts as a mirror and a diffraction grating at the same time, collecting the X-rays and diffracting them. And if we do it right, we can have the colour that we want to mostly go to the place that we want. And then obviously we're going to need a whole lot of collection optics or places for the stray X-rays to go to. So this is a diagrammatic representation. We've got our filament, electrons come out, we bend them round and hit them into our anode, which generates X-rays, and the X-rays go and hit our curved diffraction grating, which is a crystal, and the ones that we want go to our sample, and the ones that we don't want, typically the other bands, but also the general X-ray background, go somewhere else where they are disposed of. That's the ideal case. Now we've got to get to the next stage. So we've got our single colour of X-rays coming to our sample, and now we're going to get electrons out, and we need to measure their energy. We can imagine that it's comparatively easy to count electrons. We were doing that before, and we would do that with an ammeter. And if we shoot the electrons onto some kind of metal, then we will be able to measure how many electrons we have, but that doesn't tell us what their energy is. So if we're going to do it like this, we're going to have to, beforehand, sort out our electron energies so that we can measure it. Luckily, electrons are charged, so if we use a magnetic field or an electric field, we can bend the path of the electrons, and the amount that they bend depend on how fast they're going. So this is our situation that we're going to have. The electron will come along, its path will be bent by a positive and negative electrode, and it can curve round. If the electron is moving faster than the threshold, which is determined by how far apart these are and the voltages, then it will whack into the outside. If it's going slower, it will die by being dragged into the inner electrode, which is positively charged. If we can maintain the voltage for a long enough time, we can filter out only a single color energy of electrons. Of course, there is a problem in this because our electrons have to first be going all in the same direction. So we need some optics that will make them go in there. Luckily, we're not constrained to one axis, so typically we would have a wide aperture where they're going in and then they're going out apart from each other, because the electrons are being generated by an X-ray, so there's no directionality to them. We know where they're coming from, that's where the beam hits, but we don't know which direction they're going in. And if we take the ones that are going in a fan in one plane, we can insert them into a quarter or a half of a ball filter in this case, and it doesn't matter which way they're going. In that case, they will still come out of our filter. If we now sweep the voltage on this filter, we can measure different frequencies at different times, which is similar to the technology of UV-vis spectroscopy, where we had a diffraction grating and we rotated it to sweep the frequency of the light. In this case, we're sweeping the energy of the electrons. This is one way to do it. It's not the only way, but it's one way to do it, and it's comparatively easy to do. The optics on the front end to get the electrons to go into the correct orientation, and the optics on the other end, and counting them is obviously not so easy, but this is the bit that impacts the user, because the user in this case will have to wait for longer because we're measuring one wavelength at a time compared to if we were measuring them all at the same time, but practically it's easier and cheaper to do it this way. I think that's enough content for one time, so we will stop there.